Good morning, everyone. Welcome to the AUR and our session this morning on biostatistics, and this is the research track 1. So welcome, and we have a series of talks for you this morning. They're each going to be about 20 minutes in length, and then we're going to finish with a panel discussion for about 10 minutes. So my name is Linda Probyn. I'm from the University of Toronto, and I'm moderating the session together with Bill Auffermann, who's here, and Bill's also going to be presenting, and in fact, he is our first speaker. Bill is going to be presenting on basic concepts of statistical analysis. So I'll welcome Bill to the podium.
Let's start the timer there. Okay, good morning, everyone. How do we start this? There we go. Okay, so I'm just going to discuss some basic concepts of statistical analysis, no disclosures. And so I'm going to start off really basic, just hypothesis formation, probability theory, how those form the cornerstone of statistical analysis of data, and talk a little bit about some concepts of statistics needed to critically appraise research and perform research. So I think it's kind of important to start off with that, probability and statistics are really two sides of the same coin. For probability theory, there you're basically saying we know what the underlying laws of this physical process are, and we want to make some inferential statements, okay? That would be like saying we have a fair coin, we toss it a few times, what result will we are likely to receive? Statistics is the flip side of that, pun entirely intended, where let's say you've got a coin, and you want to know, is it a fair coin? Is the probability of the coin landing on either side 50%, or is it different? There you toss the coin a bunch of times, record your results, and use statistics to determine what the probabilistic laws are governing that process. So really, I think most good research should start with a hypothesis formation and a good hypothesis formation. Hypothesis is a proposed explanation for a phenomenon, and it's a key aspect, I think, of good research is having a good hypothesis, which is often paired with its logical opposite. So very often the null hypothesis is, the default hypothesis that basically nothing is happening is often the way it's phrased, some variant thereof, and the alternative is its logical complement. So as an example of hypothesis, and so when you construct a hypothesis, it should address the question of interest, and this is important, it should be testable. I've seen many cases where hypotheses are stated in such a way that it's not immediately apparent how they will be tested. And a clear statement of hypothesis is critical for both performing and appraising research. So consider an example of this hypothesis here. The medication does or does not reduce blood pressure. Well, you kind of know what they're trying to do, but they don't explicitly state how they're going to test this, so this is not immediately testable. I would argue that a better hypothesis is to say that the mean blood pressure in group 2, is equal to the mean blood pressure in group 1, or the alternative that the mean blood pressure in the treatment group 2, is lower than in group 1. Now, I personally like to take this a step further to here, well, I'll actually state when I'm stating my hypothesis exactly what we're measuring, where here we define the mean blood pressure as 1/3 systolic plus 2/3 diastolic blood pressure. Now, there's a reason for that. And I've seen this happen. I'm kind of curious. Has anyone ever collected data for an experiment and then realized you didn't collect all the data you needed? So a lot of hands going up. And so it's not possible always to completely get away from that, but if one clearly states their hypothesis, okay, exactly what we want to test, exactly how we want to test it, then the data you need to collect becomes more obvious, okay? And things can happen down the road. You realize you didn't ask the right question in the first place, but having a clearly defined hypothesis, including how you plan to calculate, some of your parameters, is really helpful to make sure you acquire adequate data. So now we're going to talk a little bit about probability theory. And probability relates to the likelihood of an event occurring. And this basically assumes, as I said before, that you understand the physical laws governing that process. The probability of certain events can often be modeled by what's called a probability distribution function. Okay? And so basically what these distribution functions show are the probability of some value x containing some value from minus infinity to infinity. The area under this curve is 1, and so that's why if you look at the probability of, let's say, some value x, you can say over all values it's 1, and over a particular range of values you can actually quantify what the probability of observing a certain outcome will be. And this is very important when making inferential statements, which we'll discuss later. And there are many different shapes of probability distributions. The one you see here, I'm sure you're all familiar with. It's the normal or Gaussian distribution. And when one knows what the shape of the distribution is, you can actually calculate the result of obtaining a certain result or range of results. Now, when performing and evaluating research, it's very important that the data be modeled correctly. So when you're like doing a statistical test that will often assume that the data has a certain distribution, it's really important just to confirm that the data actually has the distribution you think it is going to have. I know I've seen cases where, you think your data has a normal distribution, but when you actually look, it actually has a skewed distribution, or I've even seen cases of bimodal distributions. So it's very important that when you're actually doing your statistical analysis that you make sure that your data actually looks like what you think it looks like. And a very helpful way of doing that are graphical displays of data, and we'll be chatting about those in a little bit. So now we're going to delve into statistics a little bit. And statistics is the science that deals with collection of data analysis. And the way I really personally like to think of statistics is it provides a summary of your data. So for historically data sets were single variable, bivariate. Now with big data, you can have thousands of variables. And this is one of the reasons why using like machine learning algorithms has become so popular, because they're much easier for them to go through large data sets. And what they actually do is similar to what your conventional statistics do, is they provide a summary measure of the data. They take a lot of information, they try to represent it in a simpler way that human beings can wrap our brains around a little bit easier. And appropriate application of statistics can really highlight key aspects of the data. However, incorrect application can be misleading, confusing at best, misleading at worst. And I'm sure many of you have heard the quote, there are 3 types of lies, damn lies, and statistics. Well, I would beg to differ. Statistics don't lie, but they can be very misleading if not used properly. And so there are, I like to think of statistics as basically occurring in 2 potential groups, right? You've got your qualitative statistics and your quantitative statistics. There are other ways of thinking about this, but I think this is a really way that summarizes it nicely. Your qualitative statistics are basically, I'd like to think of, you don't use them to really do hypothesis testing, but you use them to get a sense of what your data looks like. So this is an example of such a tool shown here. This would be a frequency polygon, where basically you can actually look at the distribution of your data in one dimension. And you'll note here that, it's very similar to a histogram. And you'll note here that you've got 2 curves, and they actually seem like they're fairly normally distributed, but wow, it seems like they actually have a slight difference in mean. Okay, so in this, like I said, I think when starting to do research with data, using a graphical method like this, a qualitative method, is very useful to be able to get a sense of the lay of the land and what statistical approaches may be best suited for your data. So this, like I said, we don't want to just go and just apply a statistic to data without knowing what it looks like and what its behavior is. You want to use a method like this to get a sense of what it looks like and what the best methods would be to apply. Then once you have that understanding of your data, you can apply quantitative metrics for evaluation. Shown here, a quantitative metric can be something as simple as the mean. And the selection of the statistic you use, as I said, is, I think, really important, okay? And that really should be based on the data and what you see empirically, not just on what you think the data should look like and what you want to accomplish. And so I'll show you some, like this is just, imagine once again we have a medication and we want to look at its effect on blood pressure, okay? Now there are a few ways of analyzing this data, and I'll show you 2 that I've seen used. One way is to, and I've seen this happen, where people say, well, we've got our low, moderate, and high doses of our antihypertensive. We'll look at the mean value for each group, and if we assume that the data is normally distributed, we can generate a p-value for the differences in these means, and well, mean 1 and 2 don't differ significantly, mean 2 and 3 do not differ significantly, but mean 1 and 3 differ significantly. And so I'm kind of curious, have people seen this type of analysis for continuous data before? I've seen it a few times. Whereas I would argue that for continuous data, you'd probably be better off modeling it by a regression line here, where you say that your blood pressure is a continuous function of your medication dose. all right? And so this, like I said, is just to highlight that when you're conducting an experiment, use some it's very often helpful to use some graphical method for looking at your data, trying to have the data tell you what's happening, okay? And then using the appropriate statistical test that's appropriate to that data set, okay? This is not a one-size-fits-all approach. This is a very tailored approach. And I think tends to produce the best results. And this is also how you learn about, the physical phenomena that are occurring. And this brings us to the next point here, p-values. So as I said before, if you assume that you know the physical laws governing your process, such as it's normally distributed, then you basically know what the results, probability of obtaining a certain result are. And one really thing I always kind of like to bring up is that for a continuous distribution, the probability of obtaining, let's say, a result like here of x is equal to 0.15 is, any answers out there? It's 0, right? Because it's a continuous variable. That's why for p-values of continuous variables, we actually talk about a range of probabilities, or a p-value being greater than or equal to or greater than an observed value, right? Because for your real numbers, they can be made infinitesimally small, and the probability of obtaining 1.0000, infinite zeros after it's 0. So that's why we look at probability ranges. So if we actually obtain a certain test result, let's say our test statistic has a value of 1.5, and we assume it's normally distributed, and we can actually demonstrate that it's normally distributed, and the p-value would be the probability of obtaining a result of equal to or greater than the observed result, okay? And that's kind of why we phrase it that way, and which is equal to the area of the curve more distant from the observed value of the test statistic. And as I said before, probability distribution functions are constructed such that the total area under them is 1, and the probability in a range the area in a range corresponds to the probability of observing a value in that range. And of course, so based on that, the lower the p-value, the less likely it is that your data is actually modeled under the distribution, proposed by the null hypothesis. And so the lower it is, the more likely you are to reject the null hypothesis. And by convention, p-values are taken at less than or equal to 0.05 are considered statistically significant. This is not like a natural law. This isn't just some magical number that pops up in nature like pi. This is a number that, for better or for worse, our field has selected as being what's considered appropriate for statistical significance. And this is often, often referred to the type 1 error, denoted by alpha, as the probability of rejecting the null hypothesis, given the null hypothesis is true. And so I'm going to talk a little bit about multiple comparisons now. So when one talks about a p-value, this refers to the probability of observing, a value of greater than or equal to the observed value for a single test, okay? But now what happens if you conduct multiple tests? Should this affect the type 1 error level you use for statistical significance? So what I did here was I generated, let's say we want to look at, once again, blood pressures and whether or not a medication has a statistical significance on blood pressure. So what I did here is I generated 20 randomly distributed Gaussian random variable sets with mean 0. So the process here has mean 0, and anything we see differing from that is by chance alone, okay? And so what I did was I actually computed a t-test and looked at how far the average of these randomly distributed collections differed from 0. And lo and behold, 2 of them were positive, okay? And so that was because for each of these individual tests has a 0.05% probability of being positive if the null hypothesis is positive. Since we did this 20 times by chance alone, we'd expect one of these tests to be positive, even if there was no difference. So how does one account for this? Well, there's a technique which some of you may have heard of. I really like it. It's called the Bonferroni correction. It's a very conservative correction for multiple comparisons, which assumes that each test is independent. And basically what you say is that, so I want a type 1 error level overall for all the tests I'm conducting of alpha, okay? And so you want your overall desired level here. And what you do is you divide that overall level of significance, typically 0.05, by the total number of tests, in this case 20, and you arrive at a new threshold for statistical significance as shown here. So this is the new threshold that is used for all of the tests, such that there's a 0.05% probability of any of the tests being positive. And if we apply this correction to our data set, we actually see that none of the results are statistically significant, which is what we'd hope for, right? Because I actually randomly just generated data with mean 0. And so, we really don't expect and should not see a difference. So this basically gives us the results we expect to see. And this is actually very easy to apply and very helpful in cases where you're doing a number of different comparisons. I'm going to just briefly segue into confusion tables. I'm sure many of you have seen this. You've got your actual binary state of a disease, present or absent, and the test results, positive or negative. You can derive certain parameters, which I'm not going to go into how we compute them in detail, but I will just state that sensitivity and specificity are often used because they are not affected by the prevalence in the disease population, and they are often used for that reason, for evaluating how good a statistical test or diagnostic test is, or an individual is, for, like, say, reading studies, for example. Now, the ideal test would have, sensitivity of 1 and specificity of 1. That's generally not the case, right? Very often there's a compromise between sensitivity and specificity, and you have to make a selection on which is the best test to choose in a given instance. Well, it turns out that, I'm sure many of you know, there's a way of evaluating tests, when you can compare both sensitivity and specificity. Often what we use is called ROC analysis. And basically what we do here is we look at the true and false positive fractions, in which the sensitivity and specificity are basically functions of the true and false positive fractions. And we look at how they vary with the confidence. So basically we have a test or reader look at a set of images. Is there an abnormality present, yes or no? And how confident are you of that? And we plot those confidence levels versus their true and false positive fractions, and we get a curve. And the figure of merit that is often used for ROC analysis is called the area under the curve. And so this is what one often uses when we're quantifying how well a diagnostic test, statistical test, or individual is for identification of a disease process. Now, this is often also used from comparing different tests, readers. And if you have two different readers or statistical tests and they have two different ROC curves, it turns out that if the curves do not cross, the test with the greater area under the curve is the superior test. If the curves cross, it becomes a little bit more complicated. Generally speaking, the test with the higher area under the curve is generally the better test, or if you've got two people, two readers looking at images, the person with the higher area under the curve would be the overall more effective reader. So now, ROC analysis doesn't incorporate localization of an abnormality. It's just, is the abnormality present, yes or no? It's a binary decision process, which is kind of graded a little bit by confidence. But what if you want to include localization? What if you want to say, well, I want to know if they can actually localize the abnormality as well? So it turns out that there are actually a few different techniques which can be used in these instances. They would include the localization and free response ROC analysis. And LRC, they're very similar. For LRC analysis, it's used for single lesions. FROC can be used for multiple lesions. And what basically happens in these tests is, let's say you've got a chest radiograph here. There's a pulmonary nodule here in the left upper lobe. For ROC analysis, you would just say, is there a nodule present, yes or no, and what's your confidence? For LROC or FROC, you would say mark the nodule. And in this particular case, you'll notice that the green arrow, the person marked it correctly, and the red arrow, they marked it incorrectly. And this correct or incorrect localization can then be incorporated into the test, such that you include localization information when making these decisions. And so this is a little bit more complicated than your conventional ROC analysis, and there are a few other resources that I think are very helpful here. This is just a neat little radiographics article about statistics in radiology. These are two online free basic textbooks that one could use if one wants to learn more about statistics. There are tons of ones out there in print. These are two I could find that were free and are pretty good. And then these are just two papers here. ROC analysis is a little bit more specific to radiology as opposed to other fields, and so you're not as likely to see that in regular textbooks. And so here are two really nice resources about talking about ROC analysis and how to perform it, shown here. And there are also software available online for people who want to perform this analysis on their own. And so I'd like to thank you all for your time, and happy to answer one or two questions before the panel presentation if we've got a moment.
So, I know you mentioned confidence, but I find that a lot of times people are trying to make radiology studies binary so that they can analyze them with sensitivity and specificity, but there's often an indeterminate.
Mm-hmm.
So, it's negative, it's positive, or mild, early, some sort of indeterminate result. And how do you fit that into sort of ROC when there's not a binary outcome, but more of equivocal, positive, negative?
Yeah, to my knowledge, that doesn't really fit well into that framework. It's really intended for frameworks. Is there a nodule present, yes or no? Is there a cancer present, yes or no? And you would use a different test. You would actually you'd probably do more of I'm just imagining like a linear regression analysis, like with these findings, what's the probability of obtaining these findings on a continuous scale, if a disease were present at a low, mid, or high level, something like that. Yeah, but you are right. This is typically used for binary categorization.
One way of handling that would be with ROC analysis, you can actually say, I am certain of the diagnosis. I am absolutely certain it's not. And among the things, you can actually apply something like a Likert scale, and that can be used.
Okay.
Thank you very much, Bill. We're going to move on now to our next speaker, who's Mike Rosenthal, coming up to the podium here, and he's going to be discussing measurements of precision.
Thank you. Good morning, everyone. I'm Michael Rosenthal, and I'm at Brigham and Women's Hospital in Dana-Farber. I'm not a biostatistician, but I do pretend to be one in our fellowship program where I teach a course on biostats. And today I'm going to be talking about measurements of precision. I'm going to focus mostly on confidence intervals because confidence intervals capture the notion of precision in essentially all of the situations that we usually encounter. And so I want to start off with a question. So how tall is the average radiologist? It's not a terribly important question, but it is an informative question. So if we measured all of the radiologists in the world, it would take us a long time to go and rally them all together and measure them, but we would get some distribution. That would probably be a normal distribution shaped like this lovely Gaussian curve. We would know the absolute mean value and truly answer our question, and we would see that there's some distribution of heights around this mean. And in particular, about 95% of people would live within this bound between -2 standard deviations and +2 standard deviations. In the real world, it's a little bit hard to get hundreds of thousands of radiologists together to do this. And so instead, what we're going to do is sample from this population. Now, we're not going to know what the true population is when we sample, so we just have to do our best as we go along. Now, in this particular example, I've chosen 3 randomly sampled individuals here. If we take these 3 individuals, we might get a sample mean somewhere in here, maybe a little bit more off to the side. That is going to be the best estimate of the true population mean that we have based on the data that we have available in that sample. Now, as we add more data, our sample becomes more representative of the true population that we're interested in. So we add a couple more people. Those random samples happen to be on the high end of the curve, and so now our sample mean has shifted to the high end. We add a few more people, and now our sample mean is regressing closer to the true population mean. So in sample populations, in research data, most of our research data just represents a sample of a larger population of interest. We use statistics on that sample to estimate values from the full population, but these estimates are imperfect, and there are a lot of different features that go into how imperfect those estimates might be. Now, in most of this talk, I'm going to avoid going into equations because it can become very mind-numbing quickly, but I'm going to talk about this concept from the perspective of the normal distribution because I think that it's informative of how confidence intervals generally are derived. So, as I mentioned, if we sample everyone in a population, we get the absolute true population distribution, and we can speak of the true population mean and the true population standard deviation. And this is what would happen if we measured all of the radiologists in the world. When we talk about samples from that population, we can talk about sample mean, and we can estimate the variance of the sample mean. So for this particular example, we might have a sample that has a mean here, and that sample has some variance to the sample itself, but that's not what we're interested in when we're trying to estimate the true sample mean. What we can do is actually say, based on the sample that we have, we can estimate the variance of that sample mean, how uncertain that sample mean is, or how much variation that sample mean is, by taking the standard deviation that we, or rather the variance that we observe within this sample population, dividing it by the number of people that we have in that sample population, and that gives us an estimate for the variance of the mean itself. Now, this is a little bit of a funny funny concept to wrap our heads around, but basically the idea is that if I go back here, I have this sample mean, I have relatively few people in a distribution, and I can say that, if the sample variance goes out here in our sample population with just 3 subjects, our estimate of where the true population mean is going to lie with respect to the sample mean is going to come out to about here. And as I add in more people, our estimate of where that population mean might lie with regard to our sample mean is going to narrow in more and more. And so as we add larger and larger populations, our sample mean converges asymptotically towards our population mean. And this is very important to understand because it explains one of the reasons that we're so concerned with sample size in our population estimates. So there are 2 ways that we can get our sample mean to be close to our population mean. One is to add lots of samples. The more samples we add, the closer we get, and it's going to approach the population mean with square roots of the number of samples in there. The other is to have more precise data. So if you have less variance in your sample data, then your variance of your sample mean is going to go down. Now, obviously, we can't do anything about the population variance. It is what it is. We can't make people be more consistent in size. The per-Christie's approach doesn't really work in the real world. However, what we can do is have better measurements. So if you estimate people's height using just a kind of gestalt looking out in the crowd, that's going to give you a lot of variance in your measurement that's going to add to the uncertainty in your sample population. If you use very precise laser measurements of every individual, you're going to get very precise measurements, and you're going to have a variance that approaches that of the true population that you're interested in, and that's going to minimize the variance in your sample mean. So how we calculate confidence intervals really varies with the characteristics of the data that we're analyzing. This is easiest with parameterized distributions like normal distributions. If we do our histograms, as Bill just mentioned, and you see a nice normally distributed distribution, you do a test of normality, it's normally distributed, you can confidently use confidence intervals that are based on normal populations. Sometimes you have other populations, like we'll talk a bit about Poisson populations. There are situations in which we can choose different kinds of confidence intervals for more complicated data. We may be able to use exact confidence intervals. We may be able to use approximated confidence intervals. The reasons to do that get a little bit arcane and I think are beyond this, but you'll often see these choices as being available within your statistical package. And the key thing is just to choose and describe in your methods which one is appropriate. Confidence intervals can be symmetric or asymmetric based on the assumed distribution. So if you have a normal distribution, we know that there's symmetry around the mean, and so our confidence intervals are going to be the same above and below. If we have an asymmetric Poisson distribution, the confidence intervals are different above and below. So again, with normal distributions, the confidence intervals are nice and consistent on both sides. This makes it very simple for us to describe normal confidence intervals in normal distributions, and most software packages will provide these automatically under an assumption of normality. For Poisson distributions, this gets a little bit more complicated. So a Poisson distribution is a very useful distribution when you're talking about estimates of probabilities of an event in a given interval. So the Poisson distribution basically says how many events happen in our estimated population or in our population of interest within a given period of time, and it will then give you the probability of observing some other number of events within a population. So for example, if you had 12 events, 12 lethal contrast events in your institution within a 10-year period, and you wanted to know the probability that in the next 10-year period you're only going to have 3, you could use the Poisson distribution to estimate that. The key thing about the Poisson distribution is that it's really skewed. So the peak here lies close to the number of events that were previously observed, and it falls off with a very, very long tail. So the confidence interval tends to be short on the left and long on the right. These kinds of asymmetric confidence intervals generally will not be automatically provided by a package that you're using. You're going to have to either go to a biostatistician, or you're going to have to go and specifically request these through the software package when it's possible. So for the second half of the talk, I'm going to talk about the uses of confidence intervals. There are 3 main areas that we're talking about, and these are all related flavors. The first is talking about magnitude and direction of uncertainty around an estimate. So we typically are going to use error bars around a value that we're estimating. If you want to talk about mean blood pressure, we give that plus error bars around that based on our estimate of precision. We use box plots. We're going to talk about those in more detail. That's more useful for non-normally distributed data. We use numerical confidence intervals to convey this within our data tables. The overall significance of results. And by this I mean, what's the likelihood that these results represent a meaningful difference as opposed to a random difference? And again, we give error bars. The overlap or non-overlap of error bars conveys a notion of significance. We also use forest plots to depict this. Finally, we use confidence intervals to depict a range of values that should be considered as reasonable likely. This is particularly important when we're talking about odds ratios and hazard ratios, because we want to know if there are clinically important hazard ratios that might be included within the confidence interval of a value that we're estimating. We often do this using forest plots excuse me, and numerical confidence intervals. So I'm going to go through several examples of excuse me, of the depiction of confidence intervals in real data tables. So this is from a study that I did looking at features that predicted, thank you so much, features that predicted overall survival in patients with metastatic colorectal cancer. So for each of these values, there's a univariate hazard ratio, which is without adjustment, and we provide confidence intervals and then a multivariate hazard ratio. So we can see that for each of these hazard ratios, we have the central estimate here, which is the best estimate that we have based on our sample data, and then we have a 95% confidence interval provided as a range here. This hazard ratio is unitless, as is the confidence interval, and we can get a probability value here. Now you notice that the p-value for this age variable is very close to 0.05, and Bill mentioned that 0.05 is an arbitrary and somewhat magical number that we've chosen, but it is the boundary for significance that is typically seen. When you have a p-value that is close to your significance value, you expect the confidence interval to be close to whatever your null hypothesis value would be. So with hazard ratios, 1 basically means that nothing is going on. This isn't associated with the thing that I'm interested in. You can see that this confidence interval nudges right up against 1. So you can actually use the confidence interval to get a sense for the likely p-values in this data, and it makes it somewhat easy to understand where your data lies relative to significance. Now, For age, this confidence interval was pretty tightly clustered. We had a good amount of data. It wasn't particularly widely distributed. If we go down to this feature here, for example, having only peritoneal disease as a site of metastasis, you can see that our hazard ratio is pretty high, but the confidence interval is quite wide. It goes from 2.7 up to 25. And this gives you an idea that there's not tremendous precision in our estimate of this value. It's a very wide confidence interval. And in this case, that was driven by the relatively small number of people who only had peritoneal disease in this population. Similarly, down here for liver and peritoneum were not involved, meaning there were sites of metastases outside of the liver or peritoneum, and those two sites were not involved. We can see that our confidence interval goes from 0.67 to 4.3 and is non-significant. So the inclusion of 1 within that confidence interval suggests that it's not going to be significant. And the fact that it's so much wider than this population up here suggests that either we had fewer people in this group or the variance in the measurement was a lot greater. So in depicting confidence intervals, there are a few standard practices to keep in mind. The first is that we typically report 95% confidence intervals. There are reasons that you might choose other percentages, but 95% is the most typical thing to do, and we're going to report those with any important parameter estimates. So in this table from New England Journal, looking at RAS and BRAF mutation status, we see that for each estimate here, for progression-free survival, they've provided a months of progression-free survival, and they've provided a confidence interval around it. They've also provided confidence intervals in the hazard ratio. Now, this value is very interested, the months of overall survival, because we have our central value here, 28.3 months, but you see the confidence interval ranges from 23.7 to not estimable. And that means that they haven't encountered enough events to get to a 95% upper limit, and so they couldn't estimate how high the upper limit was in this value. And that is a perfectly legitimate thing to do when you're dealing with censored data like this. So we do want to specify what the confidence intervals, what significance the confidence intervals chose. So you'll see here, they do mention the 95% CI value here and here, and any non-standard interval calculation should be detailed in your methods section. Error bars are probably the simplest visual depiction of precision. This is another study looking at bold perfusion in schizophrenic patients, and they were looking particularly at two different genotypes. You can see these value bars extending down from 0 here with confidence interval error bars around there, similarly extending up here. You can see that these are non-overlapping. Just from having shown you these non-overlapping bars, I can tell you that this is a statistically significant value. Box and whisker plots play a very important role when you're dealing with non-normally distributed data. So this is another study looking at different flavors of renal tumors, AMLs and RCCs, and using chemical shift signatures. And with these box plots, you get quite a lot of data. So this central line depicts the median. The upper and lower ends of the box depict the first and third quartile boundaries. And so this gives you the sense where the bulk of this data is and where it's distributed relative to the median. And we get our 95% bounds extending out here. You also have dots added typically for extreme outliers outside of these bounding boxes. It's really amazing how much data you get out of each of these box and whisker plots, and you can get a sense for the overall lay of this data, the skewness of the data, just at a single glance. Forest plots are very important for many of the risk studies that we do, particularly in the cancer community. This is a nice forest plot from the New England Journal looking at different performance status and other issues related to cetuximab therapy in colon cancer. And what you can see here is that they've provided a hazard ratio line of 1. This is the reference line for significance. And for each of these factors that might have contributed to the significance of cetuximab impact, you can see they provide a central value estimate here, and they provide these 95% error bars around that. You can see when you have a value that a forest plot that does not cross this reference line, then that's going to be a statistically significant value. We can also see the confidence intervals provided over here to confirm. We see that for ECOG status 2, there are very wide error bars around this. They are a little bit asymmetric. This is not going to be a significant association with outcome here. So this is a great way to depict the significance of potentially dozens of values in a single very easy to read graph. This is another forest plot provided for a meta-analysis, similar concept. You can very rapidly see which genes are associated with significant differences. You can see the JAK2 mutations in both of these papers were significant on their own, and in the combined meta-analysis they were significant. The p-value confirms this, whereas for TET2 there was incomplete agreement here, so non-significant in two studies, significant in another study, and very marginal performance in the overall meta-analysis. Again, a great way to depict a lot of data in a very compact space. So I hope I've given you a little bit of a flavor for how we produce and use confidence intervals. There's really quite a lot of arcane detail that comes into the calculation of these confidence intervals, and so if you get into a situation where you're not dealing with normal distributions, my suggestion is to get a biostatistician involved so that they can help you do the right thing. Thank you.
Thank you very much, Michael. Maybe we just, if you just want to hang on, see if there's any questions. We probably have time just for one question, if there's any from the audience. Okay, we'll hold it to the panel then at the end. Great, so thank you so much, Michael. So we're going to move on to our next speaker, who is Stefan Tigges.
Close enough.
I was close. It's my Canadian accent. Who's going to be talking on analysis of Gaussian data.
So this is literally going to be the comic book approach to a lot of the stuff that you guys have already heard about. If you're interested, you could follow me on Twitter. Everything that I'm going to talk about today, I'm going to upload to my Twitter feed. So my slide deck will be on Twitter feed, and some of the comic books that I've written for my medical students. I teach this to the medical students, so you'll be getting the medical student perspective for this. I have two comics specifically on this sort of stuff, which is going to be up on my Twitter feed. So when Bill asked me to do this, I literally had to go and look up what Gaussian statistics were. So I'm probably not the best person to do this, but I'll go ahead and give it a shot anyway. So I'm going to put this in a little bit of context. When you're talking about p-values and things of that nature, what you're really doing is you're trying to come up with a way to approach claims. And for me, there's three explanations for any claims. It could be true, that's the best case scenario, or whatever claim is being made might be false. And it may be false either due to random error, which I've got up there as dumb luck, or maybe something fishy is going on. Maybe something fishy is going on purpose, or maybe by accident. And that's what I think of as bias. I'm going to spend a little bit of time talking about random error, and I'm going to talk about bias. As humans, we like to see patterns. We make all sorts of mistakes when we think that there's a pattern there, when there really isn't a pattern there. This, for example, on your left, you can see what looks like Bigfoot striding across a desert landscape, probably near Utah, where Bill lives now. But that's actually a picture from the surface of Mars. So that's not actually Bigfoot. We all know that Bigfoot actually lives somewhere in Idaho, and this is a real picture of Bigfoot right there. So first, I want to talk a little bit about bias, because it's something that I think that we forget when we talk about statistics. And I actually think that bias is much harder than statistics. Statistics, if you get in a bind, you go to a statistician and they figure it out for you. But bias is something that we're responsible for figuring out our own. So bias is any kind of systematic error in data collection and interpretation. And the cigarette ads from the 40s, 50s, and 60s are just wonderful places to look at bias. So here's Ed Sullivan, and he's going to give you some information that the Chesterfield Company has made available about the effects of cigarette smoking. So they say that they hired an ENT to look at folks and follow them for 8 months, and the ENT looked at the nose, throat, and the sinuses of people smoking Chesterfields, and by golly, didn't find any abnormalities. But of course, all of us would recognize that as being a grossly biased study. one, the ENT looked in the wrong places, and number two, it takes a lot longer for the effects of cigarette smoking to show up as opposed to just within 8 months. And poor Ed Sullivan ended up dying of esophageal carcinoma. So you can, when you sample, which is what we're going to talk about, when you sample, you can also have biased sampling. And the most famous example of biased sampling occurred in this country anyway in 1936. So in 1936, the Great Depression was going on. There was a lot of curiosity about who was going to win the election, the incumbent Franklin Roosevelt or the challenger Alf Landon. So the Literary Digest decided to see whether they could predict who was going to win. Now, if you're going to do a sample, you want to make sure that your sample accurately reflects the underlying population. Well, the Literary Digest screwed up in a big way. Now, they didn't know that they were screwing up. They thought that they had this huge sample, and they did. They had at least 1 million people in their sample, but they drew their sample from 3 sources: people who subscribed to the Literary Digest, people who owned telephones, and people who owned cars. And you can imagine in 1936, during the time when unemployment reached something like 25%, people who could afford these things, they were relatively wealthy. So wealthier people then, as now, tended to vote Republican. So they predicted a landslide victory for Alf Landon, who of course lost in a landslide victory. So you got to make sure that when you sample, that your sample is unbiased, that it correctly represents the underlying population. So Bill already talked about some of this stuff, but I'm going to hit the highlights. There's 2 types of statistics, or I think of 2 types of statistics. There's descriptive statistics, which we use. Basically, it does exactly what it says. It describes what's going on with the data. And the other type of statistics is inferential statistics, and that's what we have to use when we're trying to draw conclusions about a greater population based on a sample. And the way that we do that, if you go all the way down here, is we do something called hypothesis testing. What we do is we calculate the probability of observing the test results that we did, or the study results that we did, assuming that the null hypothesis is true. And Bill's already told you guys about the null hypothesis. If you guys slip into a coma after this slide, I will declare victory, because this slide right here, I think, gets across the most important features of statistical testing. At least I think so. So with hypothesis testing, what we're trying to figure out is whether or not the null hypothesis is true. And I'm going to go through the same example that I think Mike had with heights. Thank you. We did not coordinate this, but anyway, so what we're going to do is we're going to compare the heights of first-year medical students at Emory to the heights of NBA basketball players. So our null hypothesis would be that the heights of first-year medical students at Emory are the same as the heights, or the mean height of medical students at Emory in their first year is the same as the mean height of NBA basketball players. And we're going to assume godlike all-knowing qualities for some of these examples. And our godlike all-knowing quality for this example is that, let's say that we know that the population mean height of NBA basketball players is 190 centimeters. So our null hypothesis would be that the mean height of first-year medical students at Emory is also 190 centimeters. Let's say we measure the heights of 25 first-year medical students, and we find a mean sample height of 170 centimeters. That's different than what we expected. What we do now is we have to calculate a p-value, a probability of observing a result at least that extreme. How do we do that? Well, we take that, what we expected, 190 centimeters, we take what we observed, 170 centimeters, and we drop it into this black box of statistics right here, and we crank the handle a couple of times and a number comes out, a p-value, a probability of observing making an observation at least that extreme, assuming that the null hypothesis is true. So you always calculate a p-value assuming that the null hypothesis is true. If that p-value, if that number that pops out of the box is less than 0.05, we say we have sufficient evidence to reject the null hypothesis. In other words, the null hypothesis looks improbable. If it's greater than 0.05, we say we cannot reject the null hypothesis. Now what we're going to do is we're going to pry open that black box of statistics. It's kind of scary in there, so we're going to make this as simple as we possibly can. So the normal distribution, you guys have been familiar with that for years and years and years. That's the bell-shaped curve that we all hear about. It has a central tendency with the mean, the median, and the mode. There's also a measure of dispersion called the standard deviation. The formula is right there. I'm not going to go into that. I'm going to try to keep this as non-mathematical as possible. One of the things about one of the characteristics of the normal distribution is that 68% of your observations are going to be within one standard deviation of the central tendency, and that 95% of your data is going to be within 2 standard deviations of the central tendency. So let's say that we measure the heights of every single first-year medical student at Emory. I'm going to pretend that there's 100, there's more than that, but we're going to say it's 100 people. And let's say that we get a mean height of 170 centimeters with a standard deviation of 10 centimeters. We can actually make some predictions using those numbers. So let's say we're very cruel at Emory. We dump every single one of our first-year medical students into this green bucket, and we ask ourselves, okay, what's the probability of, at random, pulling somebody out of the bucket whose height is between 160 and 180 centimeters? Well, that's going to be 68%, right? Because 68% of our observations are going to be within one standard deviation of the mean. What's the probability of pulling somebody out of the bucket whose mean height is between 150 and 190 centimeters? Well, that's going to be 95%, because 95% of our observations are going to be within 2 standard deviations of our central tendency. What's the probability of pulling somebody out whose height is less than 150 or greater than 190 centimeters? Well, we've got 5% of the data left, right? 5% of the observations left, so it's going to be 5%. And the probability of picking somebody out whose height is going to be less than 150 centimeters is going to be 2.5%, because that's how much we've got left in this tail of the curve right here. Okay. So you can see that there's a relationship between the number of standard deviations your observation is, or from the mean, and the probability of making that observation. So what's the probability of pulling somebody out of the bucket whose height is 140 centimeters or less? Well, that's 3 standard deviations away from our mean, from our expectations. Our expected value you might think of as being 170 centimeters. And that's 3 standard deviations from what we expect, so the probability there is 0.003. In other words, very low probability. Okay, I'm going to keep going here with the heights. What we're going to do is we're going to compare the heights of people, the mean heights rather, of people in 3 different populations. We're going to compare the heights of jockeys, first-year medical students, and basketball players. And again, we're going to pretend to be at least partially all-knowing for some of these examples. So the actual population heights are listed across the top there. For jockeys, 160, for medical students, 170, and for basketball players, 190 centimeters with standard deviation of 10 centimeters in each group. So the first thing we're going to do is compare the heights of first-year medical students to NBA basketball players. We've sort of already done that. So you guys know what the null hypothesis should be here. The null hypothesis should be that the heights of first-year medical students, the mean height of first-year medical students is the same as the mean height of NBA basketball players. And we know that the mean height of NBA basketball players is 190 centimeters. We go and we find 25 first-year medical students, we measure their height, and we find a mean sample height of 170 centimeters. That's 20 centimeters different than what we expected. Now I'm going to throw a tiny little twist in here that I explain in my comic book. So if you have a problem with this, go to the comic book and look at the comic book. But we don't use this standard deviation. What we have to do is we have to calculate the standard error of the mean here. So the standard error of the mean is the standard deviation that we're going to use when we're trying to figure out how many standard deviations our observation is from our expectation. So it turns out that we're 10 standard errors of the mean away from what we expected. Our probability of being that far away, of our observation being that far away from what we expected, is less than 0.0001. So we can reject the null hypothesis at an alpha of 0.05. So in this case, these are our 100 first-year medical students. In this case, the null hypothesis is false. There really is a difference between the heights of first-year medical students and NBA basketball players. So we sample 25 first-year medical students. We find a mean height of 170 centimeters. That's 20 centimeters different than what we expected. That turns out to be 10 standard errors of the mean away from what we expected, so we have enough evidence to reject the null hypothesis. The null hypothesis is implausible. So the second thing we're going to do is compare the heights of first-year medical students at Emory to what I'm going to call Brand X Medical School. And what we're going to say is that the dean of Brand X Medical School is crazy. He makes every single first-year medical student get biometric measurements done. So we know for sure that the mean height of first-year medical students at Brand X Medical School is 170 centimeters.
We measure the heights of 25 first-year medical students at Emory, and by golly, we find a mean height of 170 centimeters. We can't reject the null hypothesis. Our null hypothesis is looking pretty plausible. So in this case, the null hypothesis is true. We've got a true negative. There's no difference between the heights of first-year medical students at Emory Medical School and Brand X Medical School. So we don't reject the null hypothesis. How could we screw this up? Remember at the very, not the very first slide, but one of the very first slides that I had talked about the three potential things that, or the three ways of looking at claims, or the three things that could happen when a claim is made. The claim could be true, or the claim could be false. And the claim could be false either because you've got random error or because you've got bias or something fishy is going on. So you can screw this up. Although the heights of first-year medical students at Emory and Brand X Medical School are the same, you can have a false positive. By the way, I hate type 1 error. Bill's a scientist. We used to kid each other, or I used to kid him. He's a scientist. He's really smart. I can't remember what type 1 error means. That doesn't mean anything to me. So I have to use the term false positive instead. So instead of using the term type 1 error, I'm going to say false positive. So you can make a false positive. You can say that there's a difference between the heights of first-year medical students at Emory and the height of first-year medical students at Brand X Medical School. You could end up with a sample that looks like this, that doesn't accurately reflect the underlying population, that overestimates the mean height among Emory medical students. And that could happen for one of two reasons. Maybe the dean's tired, okay? The dean's an important guy. He's just flown back from Shanghai. He's tired. He doesn't have a lot of time. He goes into the first room where there's a bunch of first-year medical students. He finds 25 first-year medical students. He measures their heights and gets a mean height of those medical students of 180 centimeters. Well, maybe he wandered into the basketball interest group, okay? So maybe he ended up with a sample that was biased to the tall people because he measured the heights of the basketball players in the medical school. Or maybe he just got unlucky, you know? So random error and bias are the two things that could mess you up here. And you could mistakenly say that there's a difference when there really isn't one. Okay. The last thing we're going to do is we're going to compare the heights of first-year medical students to the heights of jockeys. Again, we're going to pretend to be partially all-knowing here. Let's say that we know that the mean height of the population of jockeys is 160 centimeters. We go and we measure the heights of 25 first-year medical students. We don't really know how tall or the mean height of first-year medical students is. And we find a mean height of 170 centimeters. Again, we have to use the standard error of the mean here. We got, in other words, what we observed and what we expected is different, so we have to figure out how many standard deviations away our observation is from our expectation. Because we're dealing with population means here, we have to use the standard error of the mean. So it turns out we're 5 standard errors of the mean away from what we expected. That's a lot. So our p-value there is going to be 0.0062, so we'll reject the null hypothesis at an alpha of 0.05. So in this case, the alternative hypothesis is true. There's a difference between the heights of first-year medical students at Emory and the average height or the mean height of jockeys. And hopefully your underlying population or your sample of your underlying population will reflect this. And you'll be able to reject the null hypothesis. But of course you could screw it up. In this case, instead of making a type 1 error, you'd make a type 2 error. Again, type 2 doesn't mean anything to me. So I say that this is where you're making a false negative error. So in this case, what you're saying, what you could potentially do if you get a mean sample height of first-year medical students of 160 instead of 170 centimeters is that you could say that there is no difference when there really is one. So how could you screw this up? Okay, again, remember, there's 3 potential explanations for any claim that's being made. The claim could be true, or the claim could be false due to random error, or it could be false due to something fishy, bias. So the dean, instead of walking into the basketball interest group, could walk into the jockey interest group and end up getting the heights of people who are, you know, let's say we have 25 ex-jockeys at Emory. Probably unlikely. But you could end up with a mean sample height of 160 centimeters due to bias. Or the dean just got unlucky and ended up with a mean sample height of 160 centimeters due to random error. Those are the two ways that you could screw it up. So you wouldn't reject the null hypothesis when you really should reject the null hypothesis. Okay, so when you're looking at a clinical trial, the trial results can either be true, I guess best case scenario, or they could be false, and they could be wrong due to random error, or they could be wrong due to bias. Okay, I'm finished, and I fear your questions because I fear I may not be able to answer them, because you may just play a biostatistician, but I'm really not a biostatistician. I'm just a guy who has not yet been relieved of their biostatistics lecturing duties for the medical students because no one else wants to do it. Okay, thank you.
Thank you very much, Stefan. That was great. Thank you. I'll give you a clap there. Just in the interest of time, I think we're going to move on to our next speaker, and then we'll save the questions, if you have any, just for the end. So next is Mike Richardson, who's going to come up here, and he's going to speak to us on analysis of non-Gaussian or categorical data.
Good morning. I'm Mike Richardson, and sadly, no one has tried to buy my soul as I was putting this talk together. I do have a handout for this talk, and it'll be online, and I will show you this URL again at the end of the talk. Fear not. So let's start off with a common theme in statistics: fantasy versus reality. Fantasy is what you wish were true. Reality is what you're stuck with. So this is what you wish your data had. It's a normal distribution. It's all parametric. You have n is large or gigantic, and you have no outliers. But in reality, little or none of this may be true, sadly. Just looking at distributions of data, we would like it if everything were normally distributed, but in reality, data looks like this, or this, or this, or this, or that. So how do you deal with that? And then there's the problem of non-parametric data. And here's how you might think of parametric data. Height is a good parameter. We know that someone who's 8 feet tall is taller than someone 4 feet tall. Moreover, we know that someone who's 8 feet tall is exactly twice as tall as a 4-foot person, who is in turn twice as tall as a 2-foot person. On the other hand, suppose we're looking at this kind of data. Well, we know that 8 hurts more than 4, but is it exactly twice as painful? No, we don't know that. Then we have to consider outliers. So here's a fictitious data set I created, say the net worth of everyone in my clinic building. But why don't we just make this the net worth of everyone in this room right now? Okay, feeling comfortable with your net worth? All right. Bill Gates walks in the room. Suddenly, on average, your net worth went up to several $100 million. Now, if there were a cash machine in here, would you be able to cash out $100 million before Bill left the room? Probably not. So, even though your net worth is that high, it really isn't. And unfortunately, a lot of statistical tests are based on some property of the mean. And if it's based on property of the mean, as you can see, the mean can be distorted considerably by outliers, especially extreme outliers like that. So, how do we deal with all this stuff? We need some sort of methods that will be, that really don't care about the distribution you're using. And non-parametric methods fill that bill pretty well. You don't need to be normally distributed, or heck, you don't really need to care in general what kind of distribution you have. You can have really bizarre non-parametric scales such as this for pain, and it's just fine. Anybody wondered, but Mike, I've never used an unparametric statistic, and I've published all this stuff. Is my life just a pile of crap? Maybe not. Maybe you're still doing okay. I'm going to throw up a scary concept right here. Now, radiologists are smart. I don't mean to demean your intelligence, but I know from years of experience, when I say words like central limit theorem, that a certain part of the audience is putting their fingers in their ears going, la, 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 I can't hear you. So why don't you think of this as the central forgiveness theorem, meaning you have a certain amount of forgiveness if your n is big enough. Now, here's a bizarre-looking distribution on the left. Suppose you draw a bunch of samples from that. And then you look at the means of these samples. Well, if your n is big enough, whether you're sampling for this, or any of these things right here, those means will be distributed as a normal distribution. It's almost like magic. So there is forgiveness if your n is big enough. You might still be okay. And there's a but. If you're dealing with a lot of this stuff, the more of these things that pop up in your data, the more you should be considering a non-parametric technique. There's also part of this concept of the right tool for the right job. Now, all of us have one time or another have taken one of these and used it on one of these. You know it works, but it's not the best tool. You'd really like to have one of these as well. It turns out if you've been trained on parametric tests like Pearson correlations and paired t-tests and ANOVAs, there are non-parametric correlates that work just fine. There's also this principle. Ever heard of the Ton-Stoffel principle? Well, you might be thinking, well, gee, Mike, why not just use non-parametrics on everything? Well, Ton-Stoffel stands for there ain't no such thing as a free lunch. Let's suppose you have that rarest of all rare things, your data actually is normally distributed. Then it turns out that standard parametric tests do a great job. They're very powerful. If you try to use a non-parametric test on a normal distribution, you may not get as good results. So you may be trying to use a wrench where you need actually a pair of pliers. So let's see how that works out. Here I've created two artificial data sets. There's the red data and the blue data. And since I constructed this data set, I know that they're from a normal distribution. And I know that their means differ by about 0.3%. And just looking at it, they look almost identical, but since I have 10,000 subjects in each of these trials, if I throw a paired t-test at it, voila, they're statistically significantly different. Suppose I throw in the non-parametric correlate of the Wilcoxon. So its p-value is a little higher, so I was trying to use the wrong tool at the right time. But in general, non-parametric tests will work in most situations in finding a significant drop in power will be rare. Okay, so if any of this is wrong with your data, use one of these. Move on to a different kind of data, categorical data. This is a little different. So far, we've been talking about parametric things like height, where you have this continuous distribution. Categorical data, you tend to be limited. For example, maybe you're so limited there's only two possible values. Like traditionally, we talk about genders being male or female. Outcome, maybe life or death, disease, plus or minus, pregnancy, plus or minus. No in-between states. Sometimes we have more possibilities like ice cream or t-shirt sizes. So how do you handle categorical data like this? A lot of this kind of data you can summarize it nicely in a 2x2 table like this. And we also call these sometimes contingency tables. So how do we analyze a 2x2 table or a contingency table? Well, first, there's a main question we want to answer here. Are the rows associated with the columns? In other words, is smoking associated with lung cancer in this case? And there's two measures we'd like to look at. First of all is there some statistical significance? Secondly, is there a clinical significance? So how do we do that? This is actual data, maybe one of the very first studies that actually showed there was a significant association with smoking. And the way we want to measure that clinical significance is using the odds ratio. Okay, how do you calculate odds ratio? It turns out in a 2x2 table, this is actually pretty easy. As the name implies, a ratio, it's something over something else. And the first something is just the product of one of those diagonals there, the first diagonal. The thing on the bottom is going to be the other diagonal. And that works out to about 3. And what does that 3 mean? Basically, it's the odds of disease with exposure over the odds without exposure. So in this case, it turns out that the odds of getting cancer if you're a smoker are about 3 times that of a non-smoker. Is that significant? Yeah, I think it is. suppose you were still a resident. I know you're not, but suppose you were, and you were studying for boards and you said, man, I think I'm set for boards. And then an ad comes out in the paper and said, we have a statistically a proven effect of our boards review course here. Your odds of passing will be 3 times higher if you attend our course. You would go to that course, wouldn't you? Sure. Okay, now, next thing we want to know, is this statistically significant? For that, the classical method of doing this would be a chi-square test. I won't go through the details, but just magically appears here on the screen. And this is a ludicrously low p-value, so we know that our data here is not only, we have a strong clinical association, we also have a strong statistical significance. Swell. Well, what can go wrong with this? Well, so far we're assuming, if we're doing a chi-square statistic, that our data in this table is following a chi-square distribution, but that may not be true. Sometimes they can veer wildly away from that. For example, if you have a cell in your 2x2 table that's less than 5, I've constructed one for you here. Here's this totally made up bogus data trying to associate stool helium levels with colon cancer. And notice there's a cell there that's less than 5, a lot less than 5. If we calculate the conventional chi-square test, we say, 0.087. Well, that's maybe not completely clinically significant, but if you think, well, maybe I'm using the wrong test, are there tests you could use that would sneer at the idea of sparse cells? Yes, there are. There's things called exact permutation tests. So we run one of those, and by the way, there are exact permutation versions of almost every stat you commonly use now. How many of you use R? Can I have an amen? Amen. Yes, and if you're not using R, dude, why aren't you using R? There's a package called Coin that will let you do exact permutation values of all your old friends. Okay, if we run one of those, we find a much lower p-value and say, maybe we're getting considerable distortion of our probability here by having this sparse cell. Well, what if your contingency table is a little bigger than 2x2? What then? For example, maybe we want to look at the possibilities of lung cancer in smokers and vapors and smokeless tobacco. Or maybe we want a little more even sophisticated model so that cancer is not only a function of smoking, but also age and gender and maybe asbestos exposure. What do you do then? The easiest way is to use what's called logistic regression. It'll handle all of these things. And let's take a particular data set. This is a well-known data set, the Titanic survival data set. Here's our model. Your odds of survival is a function of what class ticket you bought, your gender, your age, whether you had siblings on board, parents on board, how much you paid for your fare, and where you embarked. Let's see how that works out. Again, I'm going to wave my hands here, and a logistic regression is magically done. Here's a huge pile of numbers here, but notice off to the right there, there's a bunch of little stars. That's the first thing that tells you, look at only these variables. These are the ones that are statistically significant. Now, rather than sift through this stack of data here, I'm going to magically convert the two lists of blue numbers closest to me into a table of odds ratios. Okay, odds ratios and their confidence intervals. Now, you probably heard the old saying, when your ship's going down, women and children first. Let's see if that actually came true on the Titanic. Well, here we see an odds ratio. If you're male, your odds of surviving are about 1/16 of that of a woman. So, yep, they were letting the women on the lifeboats first. How about age? Well, we see that that is statistically significant. For every additional year of life, your odds of surviving go down about 4%. So it looks like, indeed, women and children first was the operational dictum. If you had a sibling or spouse on board, that was also significant. It would drop your survival odds about 25%. And you can imagine that if you and your spouse get to the lifeboat and there's only one slot left, maybe one of you doesn't want to leave the other one behind. This is a really compelling one right here, the class of your ticket. Look at those odds ratios. If you had a first class ticket, your odds of surviving were about 1 in 3. Second class ticket plunges to about 1 in 9. Third class, about 1 in 26. Now, what's one of the nice features about odds ratios here is that we can combine them to figure out other things that might be of interest, such as comparing the odds of a first-class woman versus a third-class man. Turns out all we have to do is multiply these odds ratios right here, and you find out that the odds of a man in third class survive are about 1/400th that of a first-class woman. Pretty striking. I pointed this statistic out to some members of my family. My wife's grandfather was actually on the Titanic in third class. They're well aware that how rare it was that for someone to survive that category, and this just points it out even more starkly. So let me conclude here. This is real life. This is what your data looks like. Maybe it'll be one of these, you probably don't know what it'll be. Maybe you can do a histogram and you say, oh my God, it's that yellow thing, or it's that double humped red thing. You might find some scale like this, a Likert scale of pain or something else. You could use an unparametric test to handle this kind of data. They are your pals. The exact permutation tests are your pals also, and you can have them, or we'll do it for you. Here are unparametric correlates of all your old friends. Here are some of the exact permutation correlates of your old friends. I'll talk briefly about categorical data, such as this. Generally, some form of the chi-square test if you're just about a 2x2. Personally, I would use the exact permutation variety. We talked about if you have a much more complex model, use logistic regression. So we'll pause now for wild applause. Thank you. Here's the handout URL, and any questions?
Okay, great. Thank you very much, Mike. So we have about 10 minutes, and I'm going to ask the 4 speakers to come up here. We have 3 chairs, but maybe someone could stand. And we'll just, we have time now for some extra questions or, just we'll wait till they come on up.
Nobody's going to sit.
So no one's, they're all very polite. So we'll just open it up to the audience now. Do you have any questions for any of the 4 speakers?
Can you describe again how you calculate the standard error of the mean?
That's in the slide deck. Basically what you do is you take the standard deviation and you divide it by the square root of the number of your, divide it by the square root of your sample space.
Any other questions? Yeah.
Mike, why wouldn't you use the exact form of the chi-square?
I'll just repeat it.
Why would I not use the exact form? I would use the exact form.
So just, if it's not implemented, you wouldn't use it, but it's there, you use it.
If there is an implementation, sure, that would be the better way to do it. Why did they not use it in the old days? Because they didn't have computers. They had to do it by hand. Now we have computers, so we do it the right way.
So for 2x2 tables, you can always get away with the Fisher's exact test because it's calculable. But when you get into larger tables, like 4x5 tables, it becomes computationally intractable to get an exact value. And so there will be a point at which your statistical package says, no, sorry, it's not happening.
Yep. Just,
How do you treat Likert scale data? Do you treat it as continuous or categorical? I assume it's continuous, you do non-parametric, but
It's sort of what you might call a semi-quantitative scale, a Likert scale, and non-parametrics will handle that just fine. You know that, again, a 5 is higher than a 2. It doesn't necessarily have to be 2.5 times. You just know it's bigger or worse or stronger than a 2, and you don't have to worry about it.
And it's generally better to, as he said, to use the non-parametric test with Likerts unless you have really good data suggesting that your readers were very consistent in their application of Likert scales, because often people like to cluster around 2, 3, 4, or 1s and 5s, depending upon their view on the world. And if they're not consistent in that, or if they're kind of skewed to one end, then your application of parametric tests to that data will give you values that have no meaning as far as what the readers were actually doing. Whereas if you go after the parametric tests, it's much more likely that you're going to get data that accurately reflects the intention of the readers.
questions? I just have a question just about some logistics about, thinking through a study and preparing for the stats. And, I've run into the problems myself where I get into the project or whatever, and then I'm kind of scuppered because I haven't got the right data, or I'm, haven't thought about the analysis. So can you just give us your opinion on when you should think through the stats and just some kind of just common sense things so you don't run into troubles when we're doing these projects. So just give us sort of some timelines and how you go about kind of planning some of these projects so you don't run into problems.
So basically, I think it really starts when you're generating your hypothesis. So, if let's, like I said, with the blood pressure analogy, you should be thinking right then and there exactly how you're going to test that and what parameters will be needed to test it and how you're going to calculate it. Like I said, things change later on. You'll realize you might have answered in spite of your best efforts and doing everything correctly, ask the wrong question. That's the nature of science, but really clearly stating what you want to test, how you're going to test it, what data you need to test it, right up front in your hypothesis will get rid of a lot of problems down the road, although not all of them.
Yes, my answer would be back to fantasy and reality. Fantasy, you'll see the statistician beforehand. You'll work all this out in advance. Reality is they will come into the statistician's office. Help me, Obi-Wan Kenobi. I've been very naughty, and here's my data, and my study's done, and I'm presenting it tomorrow. So
Exactly. That's exactly what I was referring to, the situation I've run into a couple of times, especially with some of our learners who have to present at various things. So any other questions? I'll just ask the audience one more time. Okay, I just, you've presented some amazing resources to us, so I can tell that some of these will hopefully be available to the audience. I'm sure we definitely would find these useful. So, Stefan, the comic that you were referring to, is that available for us?
And I also have a website. It's called xraycomics.com. Comics spelled with an X at the end for, of course. Well, I thought I was being whimsical, but it turns out in the 60s that meant X-rated. You'll be very disappointed if you go to my website. xraycomics.com with an X at the end, one word. And if you go to the page labeled comics, there's all sorts of stuff. Both about sensitivity, specificity, odds ratios. Our entire evidence-based medicine course I turned into comic books.
That sounds excellent. And then you've both showed some resources there as well, but yeah, maybe if anyone's interested in getting those, you can maybe just come up at the end if you didn't catch them at the time. And so if there are no other questions, we're going to be finishing up just a couple minutes early here, but I just want to thank our four speakers today, Mike, Bill, and Stefan, for talking to us. I think that was really informative, and thank you so much for coming to do that today. Give them a round of applause. They'll be up here for just a couple minutes if anyone has any questions. Thank you.